going to continue with section 3.1, talk about the applications. There are so many that we could get into, and a lot of them is money, and also talk about half-lives and things like that. So first, we're going to talk about compounding interest. There are two basic formulas that you can kind of use. There is continuously compounding interest, and then there's this compounding per amount per year. And so this is one of those different things associated with that. So if you look on this one, this is, if you hear continuously compounding interest or compounded continuously, so again, you see that word right there. People call this the PERT equation. So it's A equals P, the number E, which you've already seen the ed puzzle on that, and then raised to the RT. So RT there is an exponent. The other one is compounding a certain amount of times per year. So if you hear it's compounded 10 times, compounded monthly, compounded yearly, compounded daily, those are the ones you're going to use the other equation. So I always say, first things first, look on there, kind of see what it is. If you hear continuously compounding, you're going to use this one. If you hear compounded monthly, you're going to use the top one. So just a little bit about this. And it says it up here what they are, but I think it's worthwhile to type it out. So A is basically your account balance, or it's kind of what you end up with. So what do you come out with? Because a lot of times the question is, how much would you have after you do this? So I would say what you end up with. P is what we call the principal. And that's basically what you're starting with. It could also kind of be what you're investing. So if you say you invest this, that means you're starting with that. R, and you can kind of step here, it's the interest rate. But it has to be as a decimal. If your numbers look like they're way too big, then you more than likely didn't move it properly. Now, that kind of reminds me to tell you that if it's 3%, you have to always move that decimal to the left 2 different times. You could also take that 3 and divide it by 100, same thing. So some people like to say, well, if it's 4%, can I do 4 divided by 100? Yes, that's the same thing as moving the decimal to the left twice, which we'll talk about, but you have to make sure you move it twice as opposed to once. So either you can move it to the left twice, or you can divide that percentage by 100, and then that will get rid of that, and you can use it. N, when you see right here, it's compounding per time. So N is how many times per year. So for example, if you hear quarterly, there are 4 quarters, so N would be 4. If you hear monthly, there are 12 months a year, so N is 12. If you hear daily, there are 365 days a year, so N would be that. If you hear yearly, there's only 1 year in a year, so N equals 1. So those are the main ones that you kind of talk about. So monthly, N equals 12. Daily, N equals 365. Quarterly, N equals 4. And then lastly, your T. So T is just your time period in years. So if you hear something other than years, you need to make sure you convert it. So 18 months would be 1.5 years. So we need all these different things, and this would be worthwhile to write this stuff down, pause the video, write it down if you haven't already. We'll come back to it. Okay, so you invest $12,000 at an annual rate of 3%. Find the balance after 5 years. So if you notice right away, I see, I'm looking at this and I'm seeing the word quarterly. So that means I'm going to use that first equation. So I'm going to go back here. I'm going to use this equation right there. First things first, you got to be able to recognize that. So N, T are exponents here. Notice that N's twice. That's an R there for the interest rate. So you invest $12,000. So when you invest, that means that's your starting amount. That's your principal. So that's $2,000. At an annual rate of 3%. Now, that's not what your R value is. And so that's the kind of key thing. Your R is not that. I have to take that 3% and move the decimal twice. So some people like to put a couple of zeros here. And then where's the decimal? The decimal is always to the right if you don't see it. So move it twice. And so in that case, it's 0.03. Again, if your numbers, if your answer seems like it's way too big, then you probably didn't do that properly. And that's quarterly. So quarterly here, that means your N is going to be 4 for the 4 quarters in a year. And then up top, you have an N again, which is 4, and then times in your T, there's your 5. So the first thing I would do is kind of just start locating stuff. You can even write out everything you find. P equals 12. R equals 0.03. T is 5. Compounded quarterly tells you n equals 4. Do that first and then go from there. So what we're going to do is we're going to type that information into Desmos. And so we'll do 12,000. And then in parentheses, 1 plus 0.03 divided by 4. And the parentheses, use my exponent. And it's going to be 4 times 5, which we know is just 20. So if you do up here, do 4 times 5, that's fine, but it's easier just to do 2 times that, although it wouldn't be wrong if you didn't do that. And so here's our number right there. So we get 13,934.209. Now, we're going to round this because of cents. So I look to the right, that's a 9. That's going to be 21. So then my answer is going to be that my final amount, my account balance would be 13,934.21. So once you get a feel for it, you're kind of just using your calculator there, but it takes a little bit to get used to it. Okay, you invest $5,000 at a rate of 2.4%. Find the balance after 7 years if it's compounded continuously. So right away you see continuously. That means you're going to use that PERT equation. So you invest $5,000. That tells you what A is. So I know, that's going to tell me what my principal is, my P. So then that's going to be that. So A will equal 5,000. And then it says at an annual interest rate. So then you have just the number E. So we'll just use that as an equation. Your exponent is going to be, so this, if I move the decimal twice, so 2.4, add a couple of zeros. If I move that decimal twice, 1, 2, that's going to give you 0.024. And then you're going to times that by how many years, which in this case is 7. So there's your T. So you've got 5,000 E and then exponent of this. So same thing. So 5,000, type in E there, exponent, and I'm going to do, you can't kind of use the keyboard down here to do your times, but I can do 0.024, and then I can times that by 7 up top. Oops, get it there. And then times that. We didn't want to do that. So what we could do is we could do 0.024, and then you can times that by 7, and you'll get this number. So apparently Desmos likes me to have that. So what I'll do is I'll have that up here. So as an exponent, I'll do 0.168. So then it'll want you to do that. So then it gives you that your final amount is $5,914.68. So again, if I look right there at that 8, that's a 3, so that's going to stay 68. So I get my final amount, $5,914.68. All right, one more. So you invest $30,000, and I would suggest reading this pausing the video, reading this a couple of times, just trying it on your own, seeing if you get the right answer, see if you did it properly. Would be my suggestion. So notice that it says compounded monthly. So again, if I see compounded continuously, I'm using the PERT equation. But if I see compounded monthly, compounded quarterly, then I'm going to use the other equation. So in this case, what are you investing? What are you starting with? Well, I'm investing 30,000. And then 1 plus R, that would be 0.047 if I move the decimal twice, or if I take 4.7 divided by 100. Monthly, how many months are in a year? 12. So that's going to be a 12. And then up here is going to be a 12. And so I get that. And so now we're going to go ahead and take that and plug it back into my Desmos and see what kind of thing we can kind of get. So if I go up here, go back to my Desmos, clear this off. And one thing I can do is with that calculation of the 12 times 8, if you want to do that ahead of time, 12 times 8 is going to give you 96. So when you go to type this in and you have 30,000, and then we had 1 plus 0.047 divided by the 12 months, exponent, and then we had up top 12 times 8. Well, we just said 12 times 8 is 96, so you can get 96. And so then you can kind of see here that you'd end up with 43,661 and then 34. So again, that 3 right there, if that's a 5 or bigger, so that goes up to 34. And so final amount, and we will talk about other type of problems where it says, what would you have to invest to end up with? But that's going to involve logarithms, and we haven't gotten to that point. And so you'd end up with that. So you invest 30,000. The more you invest, the more you're going to get out of. But it's nice to have a high interest rate as well of 4.7%, depending on what the problem is. Okay, last one. So a lot of things going on. You may want to pause this video a little bit and read this multiple times. Again, there's no reason, especially with word problems, you want to make sure you read this multiple times. So in 1986, you had a nuclear reactor in Chernobyl, Soviet Union. I'm sure you've heard about that. I think there's some movies about it. So it kind of says, here's why it's uninhabited. Here's the equation. So this is a half-life problem. This is a decay problem because your value here that has the exponent is between 0 and 1, as we learned in the last video. So that means it's decaying. So this thing's going to kind of start looking at this and then curve down. So represents the amount of plutonium. So starting with 10 amount, that's where that 10 is coming from. We start with 10 pounds of it, and how much is left after. And that's what I'm saying. We're going to sketch a graph from 0 to 100,000. And so it says T is when it happened in 1986, how much will remain in the year 2020? And so we'll kind of talk about that. How many years, first off, you're going to say how many years have gone by in that case, because that's telling you what T is. So we'll go ahead and I've kind of already plotted this for us. And so this is what it looks like. Okay, can't see anything. So I'm going to have to zoom out a little bit. All right, well, that looks like a straight line. But remember, this is just going from 0 to 50 years after it happened. We want to go to something else. So if you hit this kind of wrench up there, you can change this x-axis. I can go from anywhere. If I want to, in this case, I can go to 100,000. It's like that. Now that's starting to look like a decay equation. So this one said, okay, well, how much is there after in 2020? So how many years have gone by? So you can kind of do that in head. You can say, well, 2020 minus 1986, it's 34 years. So it'd be this equation, but 34 years. And so I could change this to f of x. And so now what's f of 34? So after in 2020, there's 9.99 left of that. Think about that. After 9, how much this would be after in the year 2020? 9.99 pounds. So it started with 10, and 34 years later, you almost have all of it left, which means it's not going away, which is exactly why they had to evacuate the city. How much of the 10 pounds remain after 100,000 years? And so you're kind of doing the same thing here. So you can either do that, or we can kind of talk about it a different way too. But if I do 100,000 years after that one, same kind of scenario. After 100,000 years, we can do the same thing here. So at that point, you're left with still almost a half a pound, so 0.56. So you've got half a pound left, and that's 100,000 years later. That's a pretty ridiculous amount. So these half-life problems, that's what happens. They take a long time. A half-life is how long a substance takes for half of it to be left. And a lot of time with this radioactive substance, it takes that much time. So if the half-life, like I said, right here is probably at 24,100, that means it's going to take 24,100 years for half of it to be left, which is a very, very, very long time. And then another 24,100 years for another half of it to be left, or 2.5 pounds in that case. You could also do a problem that says, at what point, how many years would it take to go down to, let's say we went to get down to 3. So how long would it take to get down to 3? So you could say, well, when we're saying why, when would that equal 3? When would it get down to 3? Well, that would take 41,860 years in order for it to go from 10 down to 3. How long would it take to be 5? For that, because half of 10 is 5, it's going to take that half-life. So those are different ways that you can use in a few different applications that we'll talk about on exponential functions.